A very good morning to the distinguished colleagues and guests and to the session chair. My name is Dr. Abhishek Das. I'm currently working as Associate Professor and Head of the Department of Computer Science and Engineering at Alia University, Kolkata. It's a public university in India. It's an honor to be invited to the International Conference on Transdisciplinary Solutions for Ocean Challenges here at the National Kaohsiung University of Science and Technology, Taiwan. Today, I will be discussing leveraging machine learning for transdisciplinary solutions to ocean challenges. So, I'll first give. I'll go to the next slide. I'll first give the context which I'll be going through. So, it's an overview of the main sections. I'll discuss with the ocean challenges, the role of machine learning, transdisciplinary frameworks, ocean data landscape, transdisciplinary, also the data readiness challenges, ML applications spanning the health, biodiversity, pollution, maritime, and climate, the benefits of citizen science, and open platforms, and the future trends like federated machine learning and IoT, and also include the key issues like inclusivity, the bias, the interpretability, finally conclusion and the acknowledgements. Moving on, so oceans face unprecedented risks due to climate change, biodiversity loss, and overfishing. These challenges are deeply interlinked across ecological, social, and technological domains, so no field alone can solve them. Siloed approaches where marine ecologists, technologists, and policymakers act independently are inadequate. We require solutions that integrate the strength of all the relevant domains, that is, the transdisciplinary strategies. So comes the role of machine learning. Machine learning, or ML, is uniquely positioned for this challenge. ML allows us to process vast heterogeneous datasets gathered by satellites, ocean sensors, underwater drones, and ordinary citizens. ML algorithms not only find patterns and forecast trends, but also support adaptive decision making, such as real time coral reef monitoring, species tracking, and even ocean pollution detection. In this context, ML acts as a bridge connecting data. For the transdisciplinary framework, true impact is possible only when oceanography, ecology, computer science, policy, and the community all collaborate together. The resulting interdisciplinary frameworks enable a more holistic and robust understanding of ocean systems. Integration amplifies scalability and adaptability, paving the way for solutions that are both scientifically sound and socially relevant. So, the ocean data landscape. Where does all this data come from? Oceans are monitored by satellites, sonar devices, buoys, AUVs, ROVs, fisheries logs, climate models, and increasingly by citizen scientists who report local observations. A true transdisciplinary framework thrives on this diverse multi source data, which is critical for accurate monitoring and forecasting. Now, the challenges in data readiness. With opportunity comes challenges. Ocean data is extremely heterogeneous. Formats and structures differ, spatial and temporal gaps are common, and there are often too few labeled datasets for robust supervised learning. Fragmentation across institutions and nations make full integration difficult. So, advances in machine learning readiness. Thankfully, recent advances offer solutions, pre-processing pipelines, streamline data integration. Techniques like transfer learning help adapt models to limited datasets, while multimodal fusion brings together acoustic, visual, and satellite data. Synthetic data generation is bridging gaps where the real world data is scarce. So we need to remember all this, and you see how a neural network or in machine learning works with different layers, input layer, hidden layer, and once we increase these layers, from machine learning it becomes deep learning. Moving into the next slide, machine learning for ocean health monitoring. So convolution neural networks, uh, they detect the coral bleaching from underwater imagery. So take coral reefs as an example. Convolution neural networks or CNNs have proven adept at detecting coral bleaching and identifying structural anomalies from underwater imagery, enabling near real-time conservation interventions. Such methods help us prioritize actions to save endangered reef systems. As you can see in the figure, how we have shown the reefs in Vanuatu, in the Kingdom of Tonga. Moving on to the next slide, marine biodiversity tracking. So machine learning isn't limited to imagery. It also identifies the marine species from acoustic data. Recurrent neural network or RNNs analyze whale songs or fish calls, while unsupervised clustering techniques map habitats and biodiversity hotspots, directing the ecosystem management efforts. As you can see the figure, the whale songs are being identified with that orange blobs at the frequency mentioned there, which is approximately 100 hertz. Next slide is about climate impact modeling. Deep learning is also helping us forecast critical events like ocean acidification, sea level rise, and cyclones. Hybrid long short term memory networks, that is LSTM models, merge physical modeling and data driven approaches, supporting resilience planning and informing climate policy. Moving on to the next slide about smart maritime operations. Machine learning optimizes shipping routes to reduce carbon emissions, detects illegal, unreported, and unregulated fishing using satellite imagery, and assists in global maritime governance. The impact safer, greener, and more equitable use of our oceans. So you can see the global maritime routes which is identified using machine learning optimization. Next, moving on, we have the ocean pollution detection. Despite surveillance, pollution persists. CNNs trained on multispectral satellite imagery detect floating plastic debris. Drones and satellites help identify oil spills quickly, allowing for rapid responses and targeted cleanups. For the machine learning applications summary, ML applications now span across ecology, logistics, pollution control, and climate resilience. Their benefits greater efficiency, scalability, and real time intervention. ML provides actionable insights and demonstrates transformative potential for ocean management. So, we have a case study on AI OceanNet. Consider AI OceanNet, a cloud-based system integrating drones, underwater sensors, and acoustic recorders. It uses CNNs for coral health, RNNs for illegal trawling detection, and includes NOAA data for global modeling. Cloud scalability accelerates processing and alerts. As you can see on the base of the ocean, sensor nodes are there, and sensor data is being sent to the buoys, and finally even the link is there with the oil platform. The community engagement via AI OceanNet. Community participation is central. Through citizen science inputs, often via mobile apps, people can upload images, observations, and insights in real time. This enriches datasets, builds inclusivity, and fosters shared stewardship. For the cross-disciplinary integration, marine ecologists, data scientists, and environmental managers collaborate increasingly through ML-enabled platforms. This accelerates development of interpretable models and cross-field knowledge sharing. For the citizen science and platforms, initiatives like iNaturalist, eOceans, and Ocean Track enlist volunteers, many of whom are divers or local residents, to log observations. This expands the reach and granularity of marine monitoring and improves the diversity and accuracy of ML datasets. It's almost similar to Google crowdsourcing platform. Like for if you use a kind of Google Maps, you get the real-time observation of the lanes, the streets, how busy it is. So it's a similar kind of a crowdsourcing algorithm. For the open platforms for collaboration, open science is critical. Google Earth Engine allows geospatial machine learning analysis, OceanML offers pre-trained models, and Pangaea publishes environmental datasets. These resources promote reproducibility, transparency, and broad access. Going to the challenges, bias remains a thorny challenge. Most ocean datasets are biased towards the developed world, making machine learning predictions less accurate for underrepresented and vulnerable areas, especially in the global south. Addressing this requires globally equitable data strategies. Interpretability and trust. Deep learning models are often black boxes. Lack of transparency hinders policy adoption. Explainable AI is thus critical. We need interpretable models to build trust with stakeholders. In the figure, we have given a comparison graphic of the black box versus the explainable AI, that is the XAI model. For data sovereignty and equity, respecting local and indigenous knowledge is essential. Data use agreements must ensure inclusivity and transparency, protecting communities from data misuse or exclusion. Equitable governance is the foundation of long-term collaboration. Moving on to federated machine learning, which is our future. Looking ahead, federated machine learning, it enables the distributed machine learning training, keeping sensitive data local and private, which is very vital for indigenous and community data. This fosters more collaborative and inclusive global models. So this is the figure of federated network diagram with regional nodes linked to the central ML core. Also, the IoT and edge machine learning for oceans. IoT devices like smart buoys and underwater drones now come equipped with edge machine learning. They detect events and trigger real-time alerts, strengthening disaster response and adaptive management at the ecosystem level. For the generative models for ocean events, generative models such as GANs or GANs enable the simulation of rare but high impact events like tsunamis, rough waves. These are crucial for contingency planning and resilience design. So, in the figure, simulation of possible future oceanic event scenarios is provided. Alignment with the UN Ocean Decade. Our work aligns with the UN Decade of Ocean Science for Sustainable Development from 2021 to 2030, whose framework provides global partnerships. Machine learning is a key ingredient in achieving the sustainability goals set by the UN. Finally, concluding, machine learning as enabler. Machine learning is not simply a tool, it's an enabler of scalable, adaptive and ethical solutions for ocean health, sustainability, logistics, and climate mitigation. Real impact comes from integrated, cross-disciplinary, and community-driven innovation. So, finally, coming, let's work together across sectors and nations, leveraging machine learning for ocean science. My sincere thanks to my students and collaborators. So, moving on to the slide of references, you can see the references we have cited in our paper. My my PhD students and my collaborators for listening so patiently. I will be now the floor is open for questions over to the session chair. And if you have any questions, you're welcome to answer now or send me a mail, and I'll be happy to answer you back. Thank you once again.